Welcome to our webinar. Thank you for joining us today. Our webinar this morning is using Coreform Cubit scripting capabilities to study the geodynamics of a planetary satellite. We are very excited this morning to have Alexander Berne from Caltech joining us. He'll be leading the webinar. Coreform Cubit is meshing software, and it's designed for challenging simulations and difficult problems. It includes CAD import and cleanup, semi-automatic automated hex meshing, and it allows the user maximum control of mesh properties and quality. And of course, it includes Python and its own scripting language, and that's what we're going to be focusing on today.
Thank you everyone for coming. I really appreciate it. And as Kimberly said, I'm going to be talking about how I investigate the dynamics of ocean worlds, and in particular, this moon that you see on the screen called Enceladus, using Coreform Cubit. I'll note that I'm a PhD student at Caltech. I'm also an affiliate at NASA JPL. And my collaborators on this project are my supervisor, Mark Simons, who's a professor at Caltech, and James Keene, Aaron Leonard, Ryder Park, Steve Vance, who are also colleagues of mine at JPL. You can contact me on my email, which you'll see throughout this presentation. You can also see my website here, and I'll just also note that this work that I'm going to present to you is supported by a grant called NASA Finest. And yeah, I will go ahead and move on. So I'll start by talking about the problem that I'm dealing with, which involves or requires creating a forward finite element model of a planetary satellite, and discuss that problem in the context of diurnal tides and how these tides sample interior structure. I'll move on by discussing how I've developed this numerical model using first Coreform Cubit to generate meshes, and then a modified version of a finite element code called Pilot that runs these simulations. And I'll finish by talking about some of the results that I've extracted from this research. And depending on time, I'll go over the work I've already done, but if time permits, I'll go over some of the future work that I will be working on in the coming months. So I'll talk about the problem that I'm dealing with and how diurnal tides deform this body that you see on the right, known as Enceladus. So Enceladus is a moon of Saturn. It's the second smallest major moon. It has a radius of 250 kilometers. So when you think about the size of this moon, you should be thinking from the west end to the east end of Florida, or alternatively for folks living in the west, from Los Angeles to Arizona, roughly in radius. So it's quite small, but nonetheless, it is very geologically active. Its south pole has these four large linear features, which are informally known as the tiger stripes. These tiger stripes are believed to be through-going faults. They penetrate the full length of the crust, and they're fairly massive in scale relative to the size of the satellite. Just for reference, the length of each tiger stripe is about 130 kilometers, so it's a non-negligible portion of the radius of this body. The Tiger Stripe Cassini, which was a space probe that flew around Saturn for 15 years between about 2005 and 2017, took several images of the surface of Enceladus, and it also took heat flow measurements. And as you can see on the right, and Cassini found that there was a significantly elevated heat flow over these linear features called the Tiger Stripes, which is interesting. The tiger stripes are also co-local with a number of water ice jets. These are collimated jets which spew crystals into space, and form this huge water ice plume which is coming out of the south pole of the body. So here is a collage of images of the plume brightness over one orbital period. You can see on the right, this is just a collage of images from Cassini. And as you can see, the plume actually varies in brightness by about a factor of 4 over this 32.9-hour orbital period. You can see actually the data for the plume brightness. This is a collage of data from 15 years from Cassini, which shows that there's a peak in brightness around 200 degrees mean anomaly. Mean anomaly is just a a variable used to describe position in orbit. 0 degrees mean anomaly refers to the position when Enceladus is closest to Saturn, and 180 degrees is what's known as apoapse, is when Enceladus is furthest from Saturn in its elliptical orbit. I'll go into more detail as to what that means in a second, but the point of this is just to show that there's this very periodic variation in the plume brightness, and this coincidence between the periodicity of the plume brightness and the orbital period strongly suggests that diurnal tides, which are tides with Saturn, which operate over this orbital period, fundamentally regulate the geodynamics of this body. So this is really exciting, right? Because Cassini flew by. We know that there are these plumes. We believe that these plumes sample a subsurface source of water, which is at obviously above the melting point of water. And that allows us to generate missions in the future to fly through this plume and to sample it and to look for life signs. And this is a really exciting prospect, which is currently under investigation at NASA. Several mission concepts are being developed, but in order to do this, in order to fly through the plume and sample it and understand what we're sampling, we need to have a very good understanding of the plumbing of these tiger stripes and also of the structure of the crust at Enceladus. So I mentioned that tides deform this body, and I'll discuss a little bit more about what these tides are and how they operate. So Enceladus doesn't follow a perfectly circular orbit about Saturn. It follows what's called an elliptical orbit. As Enceladus moves away from Saturn and then back towards the body, it experiences this relative change in position, and this change in position creates a gravitational potential, which creates this deformation. And you'll see that these are the 2 points of interest. There's what's known as periapse, when Enceladus is closest to Saturn, and apoapse, when Enceladus is furthest from Saturn. If we look at Enceladus in a fixed frame and look at the relative motion of Saturn, we can see this tide in a little bit more detail. You'll see that as Enceladus moves about its orbit, Saturn relatively moves away and then back towards it, and it creates this sort of rotating tidal potential, which is deforming this body. And actually, we can decompose this tidal potential into several components, radial and vibrational components, which you can see in the lower part of this panel here. So why do we care about these tides? Well, I'm going to discuss how we can use these tides to better constrain the structure of the crust for the body. So Enceladus, to first order, consists of an ice shell, which is separated from an internal silicate, basically granite core, by a sandwiched liquid water ocean in between. And over the timescale of the tide, this liquid water ocean acts to essentially mechanically decouple the ice shell from the core, which means that most of the deformation of the ice shell in response to tidal forces is regulated by its structure, and in particular its thickness, which is by far the most important structural component of the ice shell regulating its deformation. You can think of the thickness as effectively a form of stiffness. If we have a smaller thickness of the ice shell, we would expect more response to a particular tidal potential, as opposed to if we had a thicker ice shell, we would have less response. So it's basically correlated with the effect of stiffness of the body. We can predict analytically what the response of Enceladus to a tide would be if the ice shell has a mean thickness and doesn't have fractures. And this is actually a well understood problem. There are analytic solutions using spectral methods or actually really just simple 1 or 2 line equations which predict this response. But the problem gets much more complicated once we include 3D structure, which we know exists for the body. So Enceladus is expected to have significant lateral variations in crustal thickness. And we know this without getting into too much detail from taking gravity measurements of the body, which show that the ice shell has to be undulating in order to create the gravitational signature that we've detected over the body. And obviously, we know that there are fractures at the South Pole, just looking at the tiger stripes. And these fractures likely have a significant impact on the deformation of the ice shell over the orbital period. So we would expect to have a response which is significantly different from the response we would expect for a shell with a mean thickness and no faults. So as I said, the structure of the ice shell fundamentally regulates the deformation in response to tides. We can decompose the ice shell into having a mean and spatially variable thickness, and also with as having these faults at the South Pole. Um, we can go to Enceladus and we can actually measure the time variable gravity and topography using probes which have radar and radar which basically, without getting into too much detail, we can use radar measurements to track the position of the surface over the orbital period, and we can also measure the time variable gravity of the satellite by having probes which fly around in orbit, and closely tracking those probes and looking for small deviations in their trajectory. We can reconstruct the time variable gravity field. And once we have these measurements of time variable gravity and topography, given a good understanding of the forward problem, that is the relationship between shell structure and these variables, we can perform an inverse problem, which is where we take these measurements and we reconstruct the shell structure. But obviously, in order to do this, we have to have a very, very good understanding of the forward problem. And in order to do that, we need a numerical model which can achieve that. Okay, so now I'm going to talk to you about how I've developed such a numerical model. First, I'm going to talk about several aspects of Cubit that I used to develop my planetary satellite, Enceladus, and which features I sort of take advantage of. And that'll be most of this section, the discussion of the section, and I'll end the section a little bit by talking about the finite element code itself and the modifications I've made to it to make it work. So I'll start by going back to this question of lateral variations in thickness. Both of these shells that you're seeing here have lateral variations in thickness, and the way we've constructed this particular model is first within Cubit, we specify a sphere, a spherical shell with an inner and outer radius. In this case, an outer radius that is the same radius as that of Enceladus, which is 252 kilometers. We specify a shell thickness, which then defines the inner radius of the body. And then once we've done that, we generate our .exo file or Exodus file and export it. And we modify the outer and inner surface of our body using a Python code, which basically just loads in the coordinates and modifies their positions and then spits out the exo file again. So the only part of Cubit that we make use of there is actually generating the initial sphere. But once we've re-uploaded our sphere to Cubit, as you can see, especially on the left here, there is significant potential for overlapping tetrahedra that we use, overlapping nodes, basically things that would result in highly malformed elements or nodes which are too close to each other, etc. So we basically use Cubit then to do a search for these malformed elements. Basically, we ask Cubit to identify any cells that have negative Jacobians and untangle them. And that allows us to actually create meshes like the one you see on the left here. And it works pretty well. So this is definitely a feature of Cubit that we enjoy using and take advantage of. And we've been able to create these really complicated geometries as a result of this functionality. So that is how we generate lateral variations of thickness with Cubit. Now I'm going to show you how we generate fault interfaces with Cubit. Very basically, I'm going to show you this video here, and you can watch it while I explain what's happening. Once we have our shell that we've generated, we use Cubit's cut feature to actually merge two geometries, one finite volume here, which we create specifying latitude and longitude points of the outer surface. We generate a finite volume, we project that finite volume into this shell that we've created, and then we cut the two, the shell and the finite volume, to create these fault interfaces. You can see this happening as we create the tiger stripes here. So here are the four main tiger stripes that we've created, and now we'll create a few of these small splays, these sort of minor faults that occur at the tips of the tiger stripes. And so there's one, and there are two more we can get created here. There we go, there's one. And you'll notice that this is all being run automatically with a journal file. So what we've done is we've written all of this in the form of a journal file, and we just directly run that journal file in batch mode. I don't usually use the GUI, but I'm using it here obviously just to show you how Cubit is creating this particular geometry. And there we have it. Once we've cut out these four faults, we have our fault interfaces, and we can upload those interfaces. We actually specify those interfaces as individual node sets within. Oh, sorry, it also meshed. Yeah, we use tetrahedron. We refine around these fault interfaces. So anyway, moving on. Once we've generated these fault interfaces, as you can see here on the left, 1, 2, 3, 4, we pull out the node sets at the interfaces, and we specify that these node sets are fault interfaces. And what happens in the finite element code is we actually run what's called a split node analysis. We duplicate the nodes along this node set, and we allow those duplicate nodes to displace relative to each other, simulate fault deformation. And without going into too much detail as to how that works, I'll just note that we allow individual split nodes to slip. And the slip that's produced by that will result in a traction in the surrounding medium. And what we do is we force that traction to cancel out the resolved traction along these fault interfaces. And that's how we simulate fault deformation using our code. So moving on, well, once we've generated lateral variations in thickness and fault interfaces using Cubit, we then run our code. We upload our code for the first time to our finite element method. We use a code called Pilot, which is a geodynamic finite element modeling software. We've actually modified Pilot extensively to do the multi-physics problem. We don't need to just solve for the equation of motion, which involves basically body forces from the gradient of a tide and also ocean traction forces at the sort of inner boundary of our geometry. But we also need to consider these other forces known as self-gravitational and topographic forces. And these two forces are actually coupled to the displacement themselves. And involves solving another equation, which is Poisson's equation. So it's a multi-physics problem, and we've used something called a Picard iteration scheme to sort of converge on solutions using. I'm not going to go into too much detail about how that works, but I'll just note that this is how our numerical method works. And once we've simulated deformation, we can get maps like the one on the left here. So this is a map of the strain that we produce by deforming this geometry with faults and thickness variations at these sort of over the. This is the strain that we produce by evaluating displacement over our geometry and evaluating the gradient of that displacement, and then taking the second invariant of the resulting strain tensor. This is actually not a particularly accurate solution for the strain, and the reason why is because we haven't really so far discussed how we do something called mesh refinement, which is basically a method to take our distribution of tetrahedra and modify the sizing of those tetrahedra according to the strain field that we've pulled out of our geometry. And once again, we use Cubit to do this mesh refinement. So you can see a workflow of how we do mesh refinement on the right here. We start by generating a mesh initially and modifying it as we see fit. We can run an initial simulation to compute the strain over the outer surface. And then we directly modify a sizing variable within EXO files and re-upload that into Cubit. And then once we re-upload it into Cubit, we delete the mesh and we remesh it. And the resulting remesh is the refined mesh. And I'll show you an example of that here. So here on the right, you can see we have refined the mesh according to where we see strain, or actually, in this case, we've refined according to the curvature of the strain field. And as you can see, we get much finer resolution. Actually, it's so fine that it's aliasing on the computer screen here a little bit around these fault interfaces. And this allows us to obviously run much more accurate computations of strain and deformation in general using our method. And so that's really cool. And this is another functionality that we've made quite a lot of use of in Cubit. So now here is our entire methodology plotted on one really complicated looking flowchart. We use Cubit for two steps at the beginning here. We make the initial mesh and we do the mesh refinement in Cubit. And if any one step in this workflow is slow, then the entire thing will be very slow, right? So we really need to have a code which is highly efficient, or at least fast enough so that we're not held up on any one step before we start running the remainder of the simulation. And we're fortunate in that Cubit is actually quite computationally efficient. It runs things in batch mode. And it meshes relatively quickly, which allows us to sort of run these repeated simulations without having any issue. So I'll talk a little bit now about the actual finite element code. We've benchmarked it against spectral methods. In the case of the upper panel here, we've developed spherically symmetric finite element code or geometry and uploaded it into our code and checked it against a spectral method called SAFTRA. It's just a code which is out there to do the same thing, but without using a finite element method. And we output these parameters called H2 and K2. These are what are known as love numbers. Don't worry about their definition for now, but just note that they're long. They're basically parameterizations of the response of a body to a tidal potential. And as you can see, comparing our numerical method FEM to sat stress, we get very good correspondence here. Part of the reason we get such good correspondence is because we have small tetrahedra that we're able to mesh, which allows us to have obviously more accurate solutions, and because of this mesh refinement scheme, which allows us to get very, very accurate solutions using our methodology. The lower panel here is using a perturbation method, an semi-analytic perturbation method developed by colleagues at University of Arizona. NM and as you can see on the NLV, MLV equals 1,0 is just one form of a perturbation to the structure. Actually, in this case, we're perturbing the shear modulus at over a function of the sphere, of something called spherical harmonics, degree 1, order 0, and looking at the change in the love number with respect to the magnitude of the perturbation on the x-axis here. The dots are our finite element code, and the solid lines are these semi-analytic spectrum method. And as you can see here, the output in terms of this function space at spherical harmonics is very close between the two methods. And once again, this is possible because we're able to do such detailed mesh refinement and because we have such small elements in our geometries that we're using. So that's the bulk of our numerical method, and now I'm going to go over some of the interesting results which have come out of this work in the last couple of years. And if I have time at the end of this presentation, I'm going to talk about some upcoming results, which we think are quite exciting. So I mentioned these love numbers. Love numbers, like I said, are just long wavelength parameterizations of the response of the body to tides. U2M and H2M respectively represent the gravitational potential at the degree 2 order M, and for the gravity and the shape H, divided by the driving potential V at the same sort of over the same function. And like I said, you can think of these parameters as effectively a stiffness of the body. As we decrease the shell thickness, we would expect to have more response, so higher U2 and higher H2, given the same V. And as a result, we would expect a higher value of K2 and H2. And you can actually see that on the right plot that I'm showing here. So what you're looking in the upper panel on the x-axis is the mean thickness of our geometries that we've created using Cubit. And on the y-axis are these love numbers, which are parameterizations of the response. And as you can see, as we decrease the value of the mean thickness, we increase the value of the response, and vice versa for thicker ice shells. But as we introduce this 3D structure, you can see several different lines which are plotted here. We have a base model, which is spherically symmetric. We have a model with lateral variations in thickness. We have a model with faults and lateral variations in thickness, and we have a model with just faults. As we incorporate this 3D structure, we effectively weaken our geometry, which means we increase the response at a given mean thickness. And what this means is that a given love number corresponds to a range of mean thicknesses here. And this is important because love numbers are observables. These are things we can actually measure using spacecraft tracking, and also measuring the change in the position of the surface of these satellites. These are well-proven methods. We've done these sorts of investigations on the moon, calculating the love numbers for this body. And these are measurements we're planning to take at Enceladus in the future with potential missions to the body. So this spread in the value of mean thickness corresponding to a particular love number is effectively a model error. It is the error that we would get if we assumed that 3D structure did not matter when we were assessing these love numbers for understanding the interior structure. And we can map this model error as a function of mean thickness for a range of mean thicknesses we would expect for the body. And what we find is that model error is less than 10% in all cases. And this is something we figured out using these 3D finite element models. And just for reference, while not negligible, a 10% error is certainly significant. It's quite a lot smaller than the error that the model error we would associate with other methods that have been used in the past to determine the mean thickness of the body. And you can see those in the upper right, libration and admittance. And they're also quite a lot smaller than the model error that we would expect for other bodies in the solar system, such as Europa, which is a moon orbiting Jupiter. So this is quite exciting, and the results of this research are currently published at JGR Planets. And please let me know if you'd like additional details, and I'd be happy to talk about it. So another interesting aspect which has come out of this research is not just characterizing the mean thickness of a particular of Enceladus using potential measurements of strain at the surface, but also interpreting strain to determine spatially variable crustal thickness. And in order to talk about this problem, I'm going to take you back to high school physics for a minute. So if we have three springs in series, and one spring has a smaller spring constant than the other springs, if we uniaxially loaded the system with a force on one end, we would expect to have more displacement and as a result, more strain along the spring with the smaller spring constant. You can effectively think of a spring constant as analogous to a shear modulus or an elastic modulus in 3D, in a 3D geometry. So if we extend this
Alex?
analogy out to, oh, yeah, go ahead. Sorry.
We have a question before you move on.
Yeah,
How do you deal with the solid fluid coupling and the model being constrained by only the Newman boundary condition?
Yeah, of course. I'm actually going to go back a few slides to explain that to you here. So we treat so you're right. There's an ocean beneath the ice shell, and the ice shell that ocean is obviously interacting with the ice shell over the tidal time scale to create deformation. We know that the fluid is essentially inviscid, so we don't necessarily need to treat the sort of viscous flow problem here. And we essentially treat the ocean as a boundary condition on this problem. So you can think of this as being analogous to if you have an ice cube in a glass of water and you push it down, you would expect a restoring force on that ice cube to push it back up. So something similar happens when you have tides. Essentially, when you have a tide, you're changing the height of the geoid or the sort of equipotential surface, basically the gravitational potential at this ice ocean boundary. You move it up. So the water in the ocean wants to move up with this change in the height of the gravitational potential. And what that effectively means is you're essentially similar to pushing the ice cube down in the water. You get this restoring force which acts on the ice shell to deform it. And obviously the ice shell doesn't move up completely in response. It has some elastic strength, so it resists this sort of buoyant restoring force via elastic deformation. So to answer your question, we treat the solid fluid coupling as basically just as a Neumann, actually not even as a Neumann, as a Dirichlet boundary condition you can see in the lower right here. We ascribe attraction, which is exactly proportional to the change in the potential associated with the tide at this location. Does that answer your question? Whoever asked it.
I think so. You can go on.
Yeah, great. Okay. Sorry. Moving on here. So yeah, like I said, we have three springs in series. We would expect more deformation along the spring with a smaller spring constant. We can extend this analogy to a 2D elastic layer, in this case, which is semi-infinite in the sort of into the page direction. If we apply a uniaxial loading to the system, we would expect that regions of this layer which are thinner would experience more strain than regions of this layer which are thicker. And this essentially means that thickness acts as a proxy for stiffness, or in this case also, which is also analogous to treating changes in thickness as changes in shear modulus for a particular layer. It's a little bit more complicated than that, and turns out that for a 3D geometry, gradients and material properties themselves act as sources of strain. So we have to be careful when doing this one-to-one interpretation of strain fields when we're trying to infer thickness. But nonetheless, taking this general methodology, applying Hooke's law, we can begin to attempt to recover crustal thickness from potential strain fields which are measured at the surface of Enceladus. So we've developed a workflow to actually attempt to see how well we can recover crustal thickness using strain fields. We don't actually have measurements of strain at the surface, but we can generate synthetic measurements using finite element models. And what we do here is we first specify an input thickness. We can simulate the tidally driven strain from that input thickness. Taking that tidally driven EOB strain field, we can recover crustal thickness using basically a crude form of Hooke's law. And then we can account for these nonlinear gradient effects by using this iterative procedure to converge on a particular crustal thickness model until we have finished our recovery. So you can see on the left, we have an input crustal thickness model. Going through this workflow, you can see we iteratively generate a crustal thickness model in the center here. This is recovered thickness, which hopefully converges towards the input crustal thickness. You can see the residual of those two fields on the right here. So I'll show you this again. As you can see, as we iterate through our procedure, we get closer and closer to the right answer on the left here. And I'll just note that every time we run an iteration, we have to mesh at least 3 times. Once we have to mesh to first generate the geometry, and then we have to mesh again to modify the geometry to basically according to the mesh refinement scheme that we discussed earlier. And then usually we refine one more time just to get a really accurate solution. So if we mesh 3 times for each iteration, that means we have to run 36 meshes using Cubit. So obviously we need to have a very efficient scheme for doing this. Otherwise, this problem would take forever. As it is, this particular recovery took 2 weeks to run. Yeah, we definitely need a good meshing software for doing this particular problem. Because of our capacity to do pretty significant mesh refinement, we can beat our error down in this problem to about 2 kilometers, 1 sigma, which relative to the mean crustal thickness of 25 kilometers is pretty good. It's about 10% error. I'm currently in the process of developing more refined methods for actually doing this problem. And I'll just note that this work is all published at Berne 2023. It's actually now published at Geophysical Research Letters. So if you'd like more information, certainly reach out to me and we can continue to discuss. And so I'll say, the last thing I'll talk about is our potential to actually investigate some of the geodynamics of these fault structures themselves using our finite element scheme here. So I mentioned the tides deform the body. They create these oscillating sort of strain which occurs. What you're looking at here is looking up at the south pole of Enceladus. And what we'd like to do is look at the relationship between this traction, which we would expect to be resolved over these fault interfaces, and the actual activity that we've observed using Cassini measurements in the past. And how we're going to do that is first we're going to look at what are the tidally varying normal tractions over these faults. What are the tidally varying shear tractions over these faults, and how do these normal and shear tractions interact with each other? And we're going to compare these fields with actual observations of plume brightness, which I mentioned at the beginning of this talk, which vary over the diurnal period. So you'll see on the left, you can see these plume brightness variations. They vary by a factor of 4 and have a peak at about 200 degrees mean anomaly. On the right, you can see normal traction, which we have modeled using our code. As you can see, we get very smooth curves here for the normal traction, and these are smooth in part because we have such high resolution around these fault interfaces that we're looking at. When we look at where we have a peak normal traction, we see that it actually occurs at 120 degrees mean anomaly and not 200 degrees mean anomaly. And the hypothesis here is if you have normal traction, that normal traction will tend to open the faults. and allow for water to rise within these structures to feed the jets and create these variations of plume brightness. So you would expect to have peak brightness when you have peak opening, but we don't actually see that. In fact, there's a fairly significant phase lag between when we have peak opening and when we have peak brightness. So what's going on here? We can look at another traction here, shear traction, and what we find is that we have two, because this is a periodic forcing, we have two peaks. First, one that occurs at about 15 degrees mean anomaly, and another that occurs at 200 degrees mean anomaly, left lateral and then right lateral shear traction. And we're getting closer now. We see that now we have at least two peaks, which are close to the right position. The right lateral shear traction peak occurs at 200 degrees mean anomaly, which is where we have a peak plume brightness. But here I'm going to look at a third traction here called the Coulomb traction. And as I mentioned before, using the split node formulation, we can actually compute the Coulomb traction and its relationship to strike slip motion, which is this sort of relative motion of these split nodes along the fault interface that we generated using Cubit. And what we find is that there are two periods where we would expect failure of these fault interfaces. One between 30 and 90 degrees mean anomaly, and another between 180 and 230 degrees mean anomaly. First in the left lateral and then in a right lateral fashion. And this is for a particular model where we've ascribed a static coefficient of friction of 0.4. So we see that these windows occur where we have peaks in the brightness, which is good. We do have a misalignment between when we have peak left lateral shear traction and this first failure window. And this sort of misalignment between the two quantities results actually in a relative decrease in the amount of strike slip motion that we get during this left lateral strike slip window relative to the right lateral window. So more on that in a second. Here is the actual simulation that we've run using our code. You can see those four fault interfaces that we generated using Cubit earlier in that animation where I was showing the journal file. I'm actually creating the interfaces. As you can see, as we move through these windows of positive Coulomb traction, what we get are first left lateral slip and then right lateral slip over these structures. This slip results in sort of this double couple, this sort of quadrupole-like displacement field at the outer surface, which is actually something which we know could be measured from a spacecraft taking measurements of surface deformation. So we've basically developed a testable hypothesis to relate the strike slip motion to jet activity. We can actually compare the measurements of jet activity that we already have. So here you're seeing plume brightness / jet activity plotted as these dots with this bounding shaded box, which shows the range in observations taken by Cassini over several years. And these black lines are the integrated strike slip motion over the faults at a particular point in time for several different models with different prescribed values of the static coefficient of friction. And what you can see here is we've got a pretty good correspondence between this right lateral strike slip motion and the peak plume brightness. And this was really exciting because to date, no study has actually confirmed or found a mechanism which shows this correspondence, which is so close. We also find that the second peak in activity, the left lateral peak, qualitatively matches where we have the smaller peak in activity. It's not perfect. We think the reason why it's not perfect is because in real life, the system is quite sensitive to the prescribed coefficient of static friction, or to the effective friction along these fault interfaces, and we find quite a significant sensitivity to the prescribed coefficient of static friction. Perhaps our model is not detailed enough, but at least to first order qualitatively, it is matching the position and height of this peak. We also compare the spatial distribution of heat flow, which you can see on the right. It's labeled data, radiated power per unit length, and the spatial distribution of strike slip motion, this time in a depth integrated sense over the tiger stripes on the left. And what we find is that there's a pretty good correspondence between these two fields, the model and the data. Globally, we see peak activity right near the South Pole. And this is just because the amplitude of the the resolved shear traction happens to be highest at this location. And for all the faults except for this third fault called chirosolstice, we see locally that we're reproducing the position of the peak heating. So that's quite exciting. Um, and we have now sort of almost concluded this work. It's something we're preparing for submission to a Nature. Uh, our going hypothesis is that we have this predicted relationship between strike slip motion and heat flow of the, slash plume brightness of the tiger stripes. The best explanation for this is that somehow the strike slip motion is regulating the jet activity. One reasonable hypothesis is that broad strike slip motion is opening these small fissures called pull-aparts, and these pull-aparts, once they're opened, allow water to rise within these cracks and feed the jets, which then feed the plume and create these variations in plume brightness. And so this is our going hypothesis, but we are currently looking further through the data to see whether or not we can match up our finite element results with these brightness observations to further confirm this hypothesis. And with that, I will just quickly conclude my presentation. I'll go back a little bit here. By noting that Coreform Cubit allows us to readily create meshes which enable easy modification of boundary locations and untangling. We have a very good capacity to create fault interfaces using Cubit, using this cut feature. We perform adaptive mesh refinement, and we run simulation in batch mode for seamless integration into our workflows, which obviously allows us to run a lot very quickly. I will also note that when I started this project, I seriously considered using Gmesh. Gmesh is a different software, but found it quite difficult to use for many reasons. Gmesh didn't allow me to do the effective untangling that I wanted to do, or to create fault interfaces, or to do this adaptive mesh refinement. And ultimately, when I went to using Qubit, I found not only that I could do these things, but when I had trouble figuring out how to do these things, I had pretty rapid support through the online forums that are maintained. So this is definitely an advantage to using Coreform Cubit, and I'm very happy to use it and plan to continue using it in the future. And with that, I will finish my webinar, and thank you very much for inviting me. And yeah, that's it.
We do have a couple of questions for you. Alexander, someone asked, if he understands correctly, you do not include the core. How does that affect your result?
So that's a great question. I mentioned earlier in this talk that over the time scale of an orbital period, the core and the ice shell are mechanically decoupled for the most part. And that is true, meaning that if the core deforms, it's not going to affect how much the ice shell deforms, because these two aren't they aren't transmitting elastic stresses to each other. That is a little bit of an oversimplification, because this is a multi-physics problem, and we are considering self-gravitation. That is, if the core changes shape, that change in shape itself will create a gravitational potential, and it will affect the amount that the ice shell itself deforms. And we've quantified the extent to which we would expect self-gravitation of the core to affect the ice shell deformation. In a very extreme case where the core is a fluid and it has absolutely no resistance to tidal forces, we would expect at most a 10% change in the effective strain of the ice shell. So we acknowledge that is something that we don't treat. Although that being said, it's not that it couldn't be treated. We just haven't taken the time to develop that core and put it into our model. If we did it, we probably wouldn't be a finite element core, because there's no need. We don't know the 3D structure of the core, so there's no need to model it as a finite element geometry, or as a mesh, which is put through a finite element code. But yes, in the future we could include it, and we would include it by accounting for the self-gravitation of that body onto the outer ice shell for a problem. So,
okay.
Thank you for the question.
Can you mention the data grid spacing and the approximate area of each of the stripes so they can get an idea of the spatial resolution you're dealing with?
Yeah, so like I said, we cut out these finite geometries from our sphere, and just for reference, these tiger stripes are about 100 kilometers in length. In this particular mesh you see on the left, actually, this is not the full resolution mesh that we typically use. We typically go for, we try to make it so that the size of tetrahedra along the tiger stripes are about 1 kilometer to 2 kilometers in side length. Um, so what that means is we have very relative to this 100-kilometer structure, we have at least 100 elements along each tiger stripe, and we maintain that resolution with depth. Um, so I hope that answers your question. Basically, the most of the computational burden for this problem is on the tiger stripes themselves, not on the rest of the geometry, but we do include the rest of the geometry just to basically in order to get accurate answers dealing with the full sphericity of this problem. You could imagine running this code with just a Cartesian cutout of the sort of South Pole, but we've actually run that problem and we find that the answers are not the answers we get from the full sphere, and the reason why they're not the same answers is because of this effective sphericity of the ice shell, which we have to include when running these simulations. So
Okay.
I hope that answers your question.
Yes, and the last question we have here is, how did you cut the sphere? Did you use the web cut plane surface?
I quite literally I actually use subtract geometries within Qubit. So I create a sphere, a spherically symmetric ice shell, or non-spherically symmetric, and I create the second geometry. I basically specify a number of points in latitude and longitude at a radius which is beyond the outer radius um, of the ice shell. I connect those dots using a line segment, um, and then I do the same thing but below the ice shell. Um, so I specify a number of points and connect those using a line segment, and then I skin the surface that's defined by those two line segments. Um, so I now have a plane which is cutting through my geometry, and what I do then is I orthogonally project that plane. So I specify a vector and I project the plane in the direction of that vector and I specify some length, and that then creates 3D geometry. And then I use the subtract. I think it's subtract feature. I think that's right in Qubit to. And the two geometries that I choose to subtract are the ice shell and this newly generated geometry. And what I'm left with is an ice shell with a hole in it at this location. And another geometry, which is the sort of filler for that hole. And I include both of those when I upload the geometry into my simulation. But the benefit of this is that I now have a plane which is defined between these two geometries, which I can then use as a fault interface. Um, so that's what I do. Yeah.
Thank you. Okay, that seems to be all the questions we have. Alexander, I'd like to thank you again for your excellent presentation. And with that, I'll thank you all, and we hope to see you at our next webinar.